Last week, I was sitting in a dimly lit office in Shenzhen with an old friend, a hardware Scot who, spends his life tracking global supply chains. He spent the first 20 minutes echoing everything you've probably read in the headlines. How the chip war was effectively over, how export bans had frozen China's AI ambitions in time, and how the gap between Silicon Valley and the rest of the world was becoming this unbridgeable chasm. He had all the logical arguments ready. Lithography bottlenecks, the memory wall, the sheer impossibility of replicating the HBM ecosystem. Then he reached into his bag and placed a heavy, unremarkable-looking module on the table. It was the Ascend 910B. He didn't say a word. He just sort of gestured for me to look closer at the packaging, specifically where the domestic high-bandwidth memory or HBM stacks were integrated. There was no giddy excitement on his face. Instead, there was a sort of quiet, almost clinical realization. He just whispered, "The spreadsheets in Washington say this shouldn't exist for another 5 years, but I just watched 10,000 of these move off the line." That moment, that jarring disconnect between the narrative of crisis and the cold, physical reality of the silicon, that's where the real story begins. We're taught to believe that power is determined by financial indices, legal frameworks, and policy papers. We've been told that a lawyer-led system of sanctions could effectively, mothball a civilization's technical evolution. But as I looked at that chip, it became so clear that we are witnessing a fundamental handoff of physical power. While one side of the world is busy debating the ethics of AI on social media or calculating the ESG scores of tech giants, the other is quietly perfecting the art of stacking billions of transistors in three-dimensional space. It's a shift from the GDP illusion to the engineering reality. It's the realization that while you can sanction a company, you cannot sanction the laws of physics, provided you have enough engineers who know how to command them. This isn't just a story about a new processor. It is the moment the semiconductor sovereignty shifted its center of gravity, and the world is about to find out what happens when hard power is no longer written in ink, but etched in silicon.
That is a powerful and I think a really necessary opening. You've just crystallized the core tension we're all facing right now, which is this failure of the narrative to keep up with the physical reality with the output.
Exactly.
We aren't talking about hypotheticals anymore or, 5-year forecasts. We're looking at an established industrial reality on the ground. So our mission in this deep dive is to unpack the evidence behind this massive technological handoff. I think we need to focus first on the concrete hardware breakthroughs, the domestic high bandwidth memory integration you mentioned. Then maybe analyze the underlying systemic divergence that allowed this to happen. And finally, look at the fallout, the chaotic global market consequences affecting everything from hyperscale data centers down to the price of the RAM in your next PC build.
Okay, let's start right there with the hardware itself. The narrative for years, certainly in Western policy circles, has been that cutting-edge AI processing would stay constrained for certain nations, and it was because they couldn't integrate two key ingredients: the logic chip itself and the highly specialized memory needed to feed it all that data. The Ascend 910AB seems to be the physical counter-argument to that whole thesis.
It's the mercurial proof. It shows that the constraints that were imposed were either misunderstood, or they were successfully mitigated through just immense industrial effort. The central finding here is clear. The Ascend 910B AI processor is moving off production lines in significant numbers, and it's equipped with fully domestic high-bandwidth memory stacks.
Which defies the timeline.
It completely defies the Western timeline, which universally placed this level of complex, high-precision integration years away. And this is critical because it's not just a prototype at a conference. It's an industrial product rolling off the line.
And when we talk about this physical capacity, we need to be really precise about what that means. It's not just the ability to design a blueprint, right?
Precisely. This is the difference between having a design capability and having manufacturing sovereignty. The Ascend 910B is the outcome of mastering the full vertical industrial chain. We're talking about everything from the crystal growth of the silicon wafers to the application of nanometer scale lithography processes. And they're doing this effectively, even leveraging older deep ultraviolet or DUV equipment to its absolute limit. And then all the way through to the advanced packaging required to physically connect the logic die and the memory stacks.
So the real breakthrough is in the integration, not necessarily in having the absolute smallest, most cutting-edge node size in the world.
That's the subtlety so many observers missed. While the leading-edge logic gate size is still a challenge, this level of packaging, this integration of the memory, is arguably a greater immediate strategic hurdle for AI systems. The Ascend 910B is a testament to a national commitment that's solidified into tangible mass manufacturing output. It proves the entire ecosystem, from precursor chemicals to final testing, is functional at scale.
And just to clear something up for our listeners, we're talking mainly about the Ascend 910B, which is the high-volume AI accelerator, but the anecdote at the start referenced the 950PR die.
Right. And that 950 family represents the newer, more advanced iteration. It means the engineering lessons they learned on the 910 are being rapidly applied and scaled across the entire product line. This pace of iteration is absolutely central to the story.
Which brings us to HBM. Why has high bandwidth memory specifically become the new strategic fortress? For decades, the focus was always on the CPU, or the GPU, the logic chip. That was the bottleneck. Why the shift to HBM in this AI arms race?
It's a fundamental shift, and it's driven by the sheer scale of modern AI workloads, especially large language models. HBM addresses what engineers call the memory wall. To get this, you have to think about the classic computer architecture, the von Neumann model, where the processor and the memory are physically separate.
Right, and the processor is always waiting for data to travel across a bus to get to it.
Exactly. As processors got faster and faster, that bus, that highway, became the bottleneck. The CPU would finish its calculation, but then it's just sitting there, idle, waiting for the next chunk of data to arrive.
It's like having a hyper-fast jet engine, but a fueling line the size of a drinking straw.
That is the perfect analogy. Traditional memory systems, like DDR DRAM, they prioritize capacity. So you get this massive reservoir of data, but the pipeline, the bandwidth, is limited. HBM solves this by radically rethinking the geometry. Instead of placing memory chips horizontally across the motherboard, HBM stacks them vertically, right next to the processor die. Often they share the same little bridge chip, an interposer.
And that vertical stacking is what gives you that incredible bandwidth.
Yes. That vertical stacking allows for thousands of simultaneous, very short connections between the memory and the logic chip. This just dramatically increases bandwidth, the width of your data pipeline by factors of 10 or more, and it drastically reduces the distance the data has to travel. This bandwidth directly dictates the effective ceiling of any modern compute system running a massive AI model. So this breakthrough, achieving these high stacking layers and the necessary bandwidth, it fundamentally breaks the old Western assumption that the East couldn't master advanced storage and packaging technology. You can't achieve sovereignty in AI by just having a powerful brain. You have to master the high-speed infrastructure that feeds that brain information at speeds that were previously unimaginable.
It sounds like an incredibly delicate, incredibly difficult manufacturing problem.
Yeah.
And I think the human element behind this massive, quiet industrial shift is what really grounds this whole abstract engineering discussion. We have to talk about the physical grit involved.
We do. We often talk about state capacity in these grand, abstract terms. But these achievements are built on the back of individual engineers solving very physical problems. Our sources detail the work of a lead thermal engineer in Dongguan, a young woman named Li. She wasn't dealing with venture capital or writing academic papers. She was overseeing the precise integration of domestic HBM onto the processor die at an advanced packaging plant.
And this is that messy physical problem solving we mentioned. You're talking about chicks stacked in layers as thin as half the width of a human hair. They need microscopic holes drilled through them for wiring, and the whole assembly has to ensure that thousands of connections don't fail under intense localized heat.
And the term for those microscopic holes is through silicon via, or TSV technology. It's a massive engineering challenge. You are literally drilling microscopic tunnels through incredibly brittle silicon, and they have to be perfectly aligned across up to 12 layers of memory and the logic die below it.
And any mistake, it ruins the whole thing.
Any misalignment, any tiny impurity, or any variation in the thermal gradient, and the whole stack fails. Li's challenge was mastering the yield rate and the thermal management for this incredibly complex vertical stacking for their HCQ 2.0 HBM.
And the anecdote we heard centers on a really critical moment, the 72-hour stress test.
Yes, this was on the first mass-produced batch, the one destined for their internal data centers. Li was monitoring the system as it ran at full capacity. And the key moment wasn't some celebratory champagne pop. It was the quiet, clinical realization that the system hit its target of 2 terabytes per second of bandwidth without a single thermal spike or failure. That was it. The engineering-centric model had moved from theory into undeniable physical reality.
The sources describe her just walking to the window and watching the sunrise, knowing that this massive strategic hurdle had just been cleared in that quiet room, that quiet competence. The prioritization of solving complex physical problems over, say, optimizing digital ad revenue or designing the next financial derivative, that is the core divergence we need to focus on.
It leads directly to the core contrast between the GDP illusion and engineering reality. This is the cold calculus of national power and strategic resilience.
Define that contrast for us in concrete terms. What exactly is the GDP illusion in the context of semiconductors?
The GDP illusion is this deeply ingrained belief that wealth and strategic power are interchangeable, that a nation's strength is accurately captured by financial metrics like GDP growth, service sector value, or stock market valuation. So, for example, $10 billion of virtual economic output derived from something like highly leveraged financial derivatives or cloud rental services or ad tech, it looks fantastic on a national balance sheet.
But it has no depth.
In a strategic conflict or a supply chain shock, its strategic depth and resilience are negligible. You can't eat financial derivatives, and you can't run an F-35 on a software-as-a-service subscription.
And the engineering reality.
The engineering reality is that hard power requires tangible assets. That value is created by the physical command of materials. So compare that virtual $10 billion to one stable, high-yield production line churning out tens of thousands of autonomous AI chips every quarter. That production line represents hard, strategic depth. It means control over your own technological destiny.
So power isn't about the valuation of a company. It's about the verifiable physical asset and the industrial capacity that creates it.
Correct. True national will must solidify into tangible assets. High-precision production machinery, defect-free lab-grown wafers, and verifiable chip yield rates that can be maintained regardless of external policy. The Ascend 910B isn't just a commercial product. It's the physical form of that national industrial will. It demonstrates that the strategic competition is shifting away from purely financial narratives and toward the cold, hard logic of industrial output capacity and technological self-sufficiency. You can apply sanctions to influence financial flows, but you cannot sanction a well-run factory once the necessary skills and supply chains are in place.
That brings us perfectly to our next section. Analyzing the systemic differences that allowed this breakthrough to occur so rapidly, really defying the timelines set by the West. This isn't just about funding. It's a difference in industrial policy and, I think, intellectual resource allocation.
This systemic divergence is perhaps the most defining characteristic of the current geopolitical era. We can illustrate it through the sobering perspective of a veteran American procurement manager named Marcus. He's based in a deindustrialized hub in the American Midwest, and he was watching the Ascend 950 launch announcement from an office that used to overlook a thriving electronic assembly line before it was moved offshore.
Right, and Marcus's perspective offers this crucial critique of American deindustrialization. He wasn't focused on Silicon Valley stock valuations. He was focused on lead times, yield, and the physical flow of materials.
He realized something crucial, that the West had become masters of the finance of chips, the valuations, the sophisticated hedging, the stock buybacks, the asset-light strategies, but had fundamentally lost the intuition for the factory floor, the process engineering required for physical creation. His frustration came from the fact that his colleagues in the finance department were celebrated for finding ways to make the balance sheet lighter, while the engineers who understood how to improve yield by 0.5% were constantly fighting for resources.
This isn't just job loss, it's a form of strategic intellectual decay.
It is. Deindustrialization is the systemic degradation of a nation's ability to solve complex, large-scale physical problems rapidly and efficiently. When you perpetually move the factory offshore, you don't just lose the building and the lower-wage jobs. You lose the cumulative tacit knowledge, the engineering intuition, and the entire specialized talent ecosystem that goes with advanced, high-precision manufacturing. That tacit knowledge is incredibly hard and incredibly slow to rebuild.
And this structural loss leads directly into how elite talent is deployed in these two different systems. Where is the absolute top-tier intelligence being focused?
Well, the allocation of elite talent reveals a massive strategic gap. In the engineer-led model we're observing, we see an intense state-directed focus of the brightest minds, the top cohort of recent graduates like Zhang, dedicated to fundamental engineering challenges.
Like what specifically?
Integrated supply chain engineering, advanced packaging, and producing ultra-pure precursors necessary for HBM, like specialty gases and high-purity chemicals.
So their ambition is directed toward creating a domestic industrial system that is totally sovereign, solving the physical bottleneck.
Exactly. Their entire career path and incentive structure reward command over the laws of physics and successful industrial output. This creates a self-reinforcing loop where increasing technical skill drives faster supply chain integration and higher yields.
Okay, now contrast that with the deployment of elite intelligence in the financialized system.
In the financialized West, a disproportionate amount of elite intelligence, we're talking the absolute top university graduates, is channeled into fields that prioritize high financial returns but generate little physical strategic depth. They are focused on designing complex algorithmic financial products, managing billion-dollar hedge funds, debating social media content policy, or ensuring rigorous ESG compliance for multinational corporations. And while these activities hold economic and social value, they do not command the laws of physics or determine technological self-sufficiency in high-stakes fields.
So the core comparison becomes pretty stark. Which intellectual configuration is better suited to commanding the physical reality of the 21st century and ensuring long-term technological survival? The system that incentivizes its best minds to optimize finance, or the system that incentivizes its best minds to optimize manufacturing yield and physical process?
The breakthrough in HBM, a purely physical, process-intensive technology, suggests the answer is already being written on the assembly line.
Which leads us to the final and perhaps most politically charged point in this section: the difference in institutional efficiency. The engineer-led model versus the lawyer-led model. The engineer-led system achieved the ascend 910B years ahead of schedule.
And the contrast in institutional efficiency is dramatic. It's often described as a dimensional reduction strike against the more procedural system. The engineer-led model is hyper-efficient, goals-driven, and resource-intensive, backed by specific national planning bodies like the Big Fund, which allocates massive capital directly and rapidly. Technical officials lead the way. They set clear, non-negotiable roadmaps for key entities. Problems get solved swiftly in the lab and on the assembly line because they have short decision chains and extremely rapid iterative correction.
Okay, but on the surface, that sounds efficient. But the lawyer-led model, which we see in the West, is predicated on checks and balances and democratic accountability. The U.S. CHIPS Act is a perfect example of this process, right?
It is. And the U.S. CHIPS Act, despite authorizing over $50 billion in funding, is mired in procedural friction. Its implementation has been consumed by multiple layers of bureaucracy and legal complexity. You have extensive congressional haggling over specific provisions, lawyer hearings to address compliance stipulations, stringent union negotiations impacting labor requirements, and intense, drawn-out state-level subsidy competitions between places like Arizona, Ohio, and New York.
But I have to push back here a little. Isn't that necessary friction, those steps, the environmental reviews, the union negotiations, the legal hearings? That's the cost of public accountability in ensuring taxpayer money is spent responsibly. Are we arguing that democracy is inherently too slow for strategic industrial planning?
Well, that is the strategic argument being asserted by those who analyze this divergence. They're not saying the accountability is bad philosophically, but they are arguing that the political and legal complexity incurs a massive cost in the form of time, the most precious resource in a technology race. So while accountability is high, strategic velocity is low. The highly efficient, goal-oriented system, even one lacking certain external checks, constitutes a dimensional reduction strike because it maximizes speed.
So the lawyer-led system is optimizing for procedural fairness and accountability.
Right.
While the engineer-led system is optimizing for speed and physical output.
Exactly. The time lost navigating the legal and political complexities of the lawyer-led model gives the engineer-led model an open window to achieve physical reality, like the mass production of the Ascend 910B, years ahead of projection. The underlying principle, they assert, is that if freedom is interpreted as the ability of entrenched vested interests, whether financial, regional, or political, to slow down strategic national progress, then that form of freedom actually ensures the system will fall behind in a hard technology race where the adversary is entirely goal-oriented. The goal of the engineer is simple: build the chip. The goal of the lawyer is complex: build the chip according to 500 pages legal stipulations.
The impact of these shifts in hard power, especially the explosion of high-speed AI chips globally, isn't confined to geopolitics. It's causing massive chaos in the consumer and industrial electronics market, specifically in memory. We are now deeply immersed in what analysts are calling the AI-driven memory supercycle, and the consequences are brutal for anyone buying a PC or running a data center.
The memory market is experiencing unprecedented turbulence, and it's directly fueled by the AI boom that needs HBM. The growth of demanding technologies like large language models and generative models requires two things at an almost unimaginable scale: high bandwidth memory, HBM, and advanced high-speed LPDDR for inference engines. Companies like NVIDIA, Amazon Web Services, and Microsoft are now buying HBM capacity at levels comparable to the entire global smartphone industry combined just a few years ago.
That scale is just staggering. And we know HBM is incredibly difficult to produce with those delicate stacking layers and the TSV technology.
It is the ultimate choke point. HBM's complex manufacturing, involving stacking layers as thin as half a human hair and getting flawless interconnectivity, it creates a high barrier to entry and makes the chips significantly more expensive than traditional memory. The demand is explosive, but the supply chain for HBM is rigid and limited, primarily confined to three major players: SK Hynix, Samsung, and Micron. They simply cannot scale capacity quickly enough to meet this demand.
Okay, so the AI giants are sucking up all the top-tier high-margin HBM. That makes sense for the high-end server market, but how does that cause a catastrophic shortage in, say, the DDR5 you'd put in a standard office PC or a mass-market server?
That is the core mechanism of the commodity DRAM crisis that's hitting us now. It's a severe, supply-driven shortage caused by a profit-maximizing decision by the memory manufacturers. They looked at the massive profit margins of HBM, which can be 5 to 10 times higher than commodity DDR DRAM, and they made a logical decision. They diverted their existing wafer capacity away from cheaper DDR production and toward the vastly more lucrative HBM and advanced LPDDR lines.
So they didn't even need to build new factories. They just changed the menu in the existing factories.
Precisely. The physical infrastructure, the expensive silicon foundries or fabs, remained the same. But the product mix was violently shifted. Even if the industry's total DRAM wafer starts remained flat or were nominally rising, the effective capacity dedicated to commodity DDR DRAM shrank suddenly and severely. This sudden reduction in supply, coupled with steady general computing demand, is why traditional memory segments are facing severe scarcity. It's what created this memory supercycle, where prices have soared, in some cases tripling year over year. It's a textbook example of a market shock driven by a high-margin product cannibalizing the commodity supply base.
Let's talk about the numbers, because they really confirm the severity of this. What data points best illustrate the sheer scale of this crisis?
The contract price data is, well, it's stark evidence. Consider the contract price for a standard 16-gigabit DDR5 chip, which is the memory used in new laptops and mid-range servers. It surged from approximately $6.84 to around $27.20 in just 3 months. That's nearly a 300% increase at the fundamental manufacturing level. This isn't just retail gouging. This is the base cost of the components skyrocketing.
And this inflation is widespread. It's not just in one segment.
Absolutely. Server DRAM, the kind that goes into cloud infrastructure that doesn't use HBM, saw prices double year over year. Even NAND flash, the memory used in SSDs and smartphones, also saw approximately 100% price hikes in parallel. And crucially, market inventory levels for DRAM, which typically sit at a comfortable 8 to 12 weeks of supply, fell to a crisis level 2 to 4 weeks by late 2025.
Wow.
When inventory drops that low, the supply chain is operating on fumes. One small factory fire or logistical hiccup could trigger massive industrial shutdowns.
It sounds like something out of a Cold War resource crisis, not a modern global electronics market. So how are companies and consumers reacting to this massive, unprecedented shortage and cost increase?
The responses across the industry show just how drastic the situation is. System builders, the companies that assemble computers, are being hit hard. For instance, CyberPower PC publicly announced price increases because they cited a dramatic 500% surge in RAM prices impacting their bill of materials, the list of components needed to build a machine.
And when memory costs go up, it disproportionately hits the final price of the product, doesn't it?
It does, because memory now consumes a much larger slice of the overall cost. PC OEMs like Dell and Lenovo signaled imminent price increases on their PCs, likely in the 15 to 20% range, because memory costs had absorbed roughly 18% of a new PC's total bill of materials, which is double the historical share. They just can't absorb that cost themselves.
And on the retail side, we're seeing measures designed to prevent panic and hoarding.
Yes. To curb hoarding, Japanese electronics shops in major hubs like Akihabara restricted purchases to just 2 to 4 memory modules per customer.
Wow.
Which effectively limits builders and small businesses. But even more drastically, Taiwanese distributors, who control the flow of components into the channel-mandated strict 1.1 bundling.
What exactly does 1.1 bundling entail?
It's a desperate allocation strategy. It means a vendor cannot purchase a memory module unless they simultaneously purchase a motherboard. This prevents vendors from just hoarding the most constrained item, the DRAM, and forces them to take the less constrained item, the motherboard, too. It controls the allocation to system builders and ensures the stock they do have is paired with complementary components. It's an extreme measure of scarcity control usually reserved for things like graphics cards during a mining boom, not standard memory.
And what about the manufacturers themselves, the memory giants? Are they rushing to ramp up commodity DDR capacity to alleviate the consumer pain?
On the contrary, they are reinforcing their pivot to the high-margin specialty segment. Micron, the third largest DRAM manufacturer, actually wound down its consumer brand, Crucial, to focus entirely on specialty DRAM segments, server memory, and mobile memory, essentially retreating from the volatile, lower-margin commodity PC space entirely. Samsung and SK Hynix are content to reap record profits from these incredibly high margins on HBM. Their strategy is crystal clear. Prioritize high margin, not high volume, for the commodity side.
So what's the prognosis? If demand is this strong and prices are this high, why aren't they just throwing money at building new DDR factories immediately? That seems like the logical, profit-driven response.
The prognosis is pretty grim for the short to medium term, precisely because building a new fab takes 4 to 5 years and billions of dollars. The industry consensus is that DRAM supply will remain tight until new, massive fab construction plans are operational. SK Hynix, for example, has announced huge multi-fab plans, but the earliest production start date for any of that new capacity is 2027, with others not ramping up until late 2028. This means shortages could extend for several years.
And the constraint here isn't just the construction time. It's this core caution, the fear of an AI bubble bursting.
This is the financial risk management at play. Memory makers are extremely hesitant to commit the massive capital required to build too much commodity DDR DRAM capacity. They remember the previous boom-bust cycles. If AI demand wanes unexpectedly, or if the market consolidates faster than anticipated, they could face severe oversupply in 2028 or 2029 and collapse back into massive losses. They're prioritizing stable, incredibly profitable margins now, even if it means a constrained supply and market pain over the high risk of catastrophic overinvestment in volume capacity. In essence, they are betting that cautious profit stability is the safest long-term strategic posture.
While the East focuses on manufacturing sovereignty and the financialized West grapples with the market consequences of this AI supercycle, we need to turn our attention to Europe. The old continent has its own legacy in the chip industry. It's home to ASML, but it has seen its overall share of global manufacturing shrink dramatically. How is Europe trying to navigate this global resource war and establish its own sovereignty?
Europe is attempting to carve out its own space through the EU Chips Act, which was formally enacted in September of 2023. This legislation signals a fundamental massive policy shift. For decades, the EU adhered strictly to free market precedent, generally forbidding state subsidies for industrial projects to prevent protectionism. The Chips Act shattered that precedent.
So they're using public funds to inject life into the semiconductor industry, mimicking the proactive industrial policy we've seen in the US and East Asia. What's the explicit, measurable goal here?
The primary stated goal is ambitious and quantitative, to increase Europe's global chip production share from the current 9% all the way to 20% by 2030. The most relevant mechanism for this is Pillar 2, which relaxes restrictions on state aid for first-of-a-kind manufacturing capacities. This is essentially the legal mechanism designed to attract leading-edge fabs, like the one Intel is planning in Magdeburg, Germany, by allowing member states to provide massive subsidies that close the cost difference between building a fab in Europe versus highly subsidized regions in Asia or the US.
But the sources indicate that Europe is facing a fundamental policy dilemma about how to spend those subsidies, a real split in strategic focus.
They face a fierce internal debate. The split is between targeting existing mainstream chip capacity, meaning mature, high-volume nodes like 28mm, 40mm, and 65mm, or dedicating the bulk of the money exclusively to attract cutting-edge technologies, such as sub-2 nanometer fabs from foreign giants like TSMC or Intel.
Why is mainstream chip capacity such a strategic priority for Europe, especially if the global narrative is always about the cutting edge?
Because mainstream nodes are the lifeblood of Europe's core industrial sectors. Think automotive, industrial controls, healthcare machinery, and power electronics. These systems like anti-lock braking systems, engine management units, or factory automation robots relied almost exclusively on rugged, reliable 28mm or 40mm chips, not 3mm processors. If Europe lacks domestic capacity for these legacy nodes, their entire manufacturing base becomes strategically vulnerable.
So, relying solely on attracting a 2nm Intel fab might give them some bragging rights, but if a supply shock hits the 28mm chips used for car safety systems, the European auto industry grinds to a halt.
Exactly. Industry voices strongly favor bolstering existing mainstream nodes because the bloc's current chip production capacity aligns with what downstream European manufacturers actually need. 3/4 of France's chip exports, for instance, already serve the domestic European market. Subsidizing only the cutting-edge smallest nodes might bring impressive headlines, but it wouldn't solve the core industrial resilience problem for sectors like Bosch or Volkswagen. It would be a prestige project, not a sovereignty solution.
This suggests that Europe really needs to leverage its existing strengths rather than trying to replicate the high-volume, leading-edge capacity of East Asia, which is a near impossible task.
Precisely. Europe maintains indispensable roles in several crucial segments of the semiconductor value chain that must be protected and bolstered. They possess ASML, which holds a global monopoly on the production of EUV lithography machines, essential for advanced nodes globally. They also have German materials providers like BASF, critical design software from Siemens, and global leadership in key vertical sectors like power and sensor chips through domestic champions like Infineon and STMicroelectronics.
So the strategy has to focus on reinforcing those unique choke points where Europe already has a leveraged advantage. How are they trying to make sure their R&D spending translates into domestic industrial strength?
The key strategy is bolstering domestic firms and nurturing vertically integrated ecosystems. We see excellent models of this already in the automotive sector. They have partnerships between research institutions like CEA-Leti, European chip makers like STMicroelectronics, and downstream players like automotive suppliers, Valeo, and manufacturers, Volkswagen.
That vertical integration model seems smart. They are sharing the immense risk of developing a new chip, but they're also ensuring the IP benefits stay local.
That's the core intent. The shared risk ensures that if the new technology fails, the financial impact is spread across the supply chain, not borne by a single startup. And crucially, it ensures that the intellectual property remains internal to the European ecosystem, bolstering their long-term competitive position.
But even with the CHIPS Act and this vertical integration model, Europe faces a persistent fundamental weakness when it comes to scale. Their chip startups often struggle to become global champions.
They absolutely do. This is Europe's Achilles heel. The inability of its promising chip startups to successfully scale. They face a steep valley of death in later stage funding. While Europe may birth a high percentage of all venture-funded startups, the funding drop-off is disastrous. Venture capital funding in Europe falls a staggering 83% from Series B funding rounds to Series E, compared to a drop of only 55% in the US. This critical lack of late-stage capital prevents these promising ideas from achieving the massive, costly scale required to become domestic champions like ASML or Infineon.
That massive capital constraint at the critical growth stage is a structural problem. How can they fix that and at the same time prevent state-funded IP from leaking to foreign competitors?
They need a deliberate protective IP policy modeled after institutions like the French CEA-Leti Research Center. Leti, which receives heavy state funding, retains ownership of key patents and grants preferential licensing terms to French and European companies over their non-European counterparts. This policy is explicitly aimed at ensuring that state-funded research results and valuable intellectual property don't immediately leak overseas and strengthen foreign competitors. It makes it financially easier for European companies to use cutting-edge research.
So if a foreign company wants to use that IP, they have to pay a much higher premium, which disincentivizes foreign acquisition of state-funded research benefits.
It creates a kind of protective tariff around intellectual capital. But to truly foster future giants, Europe needs broader structural reform that goes beyond the immediate CHIPS Act grants. The most significant blocker to late-stage funding is the massive pool of institutional investment capital that remains locked up.
You're talking about the pension funds, aren't you?
Yes. The numbers are shocking. Currently, only 0.01% of Europe's massive multi-trillion euro pension fund assets are invested in VCs.
0.01.
Yes. Compare that to 2% for some leading U.S. state pension funds. Freeing up that institutional capital to flow into VCs is absolutely essential for giving startups the late-stage funding they need to cross that valley of death. It requires tax and regulatory reform that makes it easier and more appealing for pension fund managers to allocate a fraction of their assets toward high-growth, strategic venture capital investments.
It sounds like the EU CHIPS Act is the necessary starting gun, giving them permission to engage in industrial policy again. But the true race for sovereignty will be won or lost based on their ability to create a sustainable capital and talent pipeline for those domestic champions, particularly in those crucial mature nodes.
It's the difference between writing a policy and building a self-sustaining financial ecosystem. Europe must find a solution that isn't just a temporary subsidy, but a cohesive tax, regulatory, and industrial environment that helps entrepreneurs not only innovate in a lab, but actually scale their manufacturing capacity into a global player within Europe.
We've covered a lot. The technical breakthroughs of domestic HBM, the systemic divergence in governance models, the global market consequences of the DRAM supercycle, and the complex European response. This has been a true deep dive into the technological, economic, and geopolitical consequence of this shift in chip sovereignty.
And the unifying thread connecting all of these distinct areas is the increasing, unavoidable importance of physical industrial capacity. The global chip landscape is being violently reshaped not by financial forecasts or diplomatic declarations, but by the cold, hard success of physical engineering breakthroughs, specifically the ability to produce and integrate advanced domestic HBM stacks at scale.
And we've seen the world simultaneously witnessing the rise of a focused, engineering-centric power, the Ascend 910B being the undeniable material proof of that, and the agonizing market consequences, the DRAM supercycle, caused by a decades-long strategic decision to prioritize financialization, quarterly earnings, and asset-light strategies over manufacturing resilience.
The memory supercycle, with contract DDR5 prices surging nearly 300% in a quarter and inventory dropping to crisis levels, is the direct, painful feedback loop demonstrating the fragility of the financialized system when it's faced with an industrial reality shock. This is where the paper promises of global efficiency break against the hard wall of physical constraints.
This isn't just about economic competition anymore. This is the moment when semiconductor sovereignty truly shifted its center of gravity. The future of hard power is now literally etched in silicon, governed by the cold, unyielding laws of physics and verifiable industrial capacity. This is the final reckoning of manufacturing civilization against the illusion of the virtual economy.